Hi everybody, my name is Ayslan Costa. I am a mathematical and PhD in process engineer. I have been doing my postdoctorate at EPIC, Sub-2. So this work shows the investigation of the HLD parameters on emulsion phase inversion predictor. The motivation of the study is related to the formation of emulsion in the inversion phase of the systems inside the electric submersible pumps, ESP. Reiterate that the pump efficiency is related to the fluid viscosity and depends on the water cut and the continuous phase present in the emulsion. There is a change in these operation parameters and the two affects the performance of the EPS. For the reason, it's important to know the parameters that influence the PIP in the emulsion, the oil and the water systems. In the sense, Salag and the collaborators showed that the chemistry of the systems is fundamental to understand the behavior of the systems and to make use of the thermodynamic parameter HLD, hyperphilic lipophilic deviation. The HLD depends on the chemical parameters of the system such as the EACN of the oil phase, the type of surfactant, and this concentration, the alcohol salt concentration present in the aqueous phase temperatures, among others. The study proposed to investigate whether HLD is a good parameter to improve PAP predictions model. The emulsion was synthesized using two types of oil with a viscosity of 19 and 206 cp at 25 degrees Celsius, sprayed and treated as a surfactant, and pentanol with co-surfactant with fixed concentration for determination against the point. The emulsion phase inversion was carried out following the semi-continuous phase inversion protocol developed by Salaga and collaborators, and increased the water cut value by step 5%. The water cut was defined as the water to oil ratio. The measure of emulsion phase inversion point were carried out by using an ultraturbox and two rotation speed, 6,000 rpm and 18,000 rpm at a temperature of 25 degrees Celsius. Each emulsion was first started for 13 seconds, after which its conductivity was measured in situ by a conductometer. The PIP determination were repeated 3 times for each emulsions. Then a curve fit was proposed to the data present in the above diagrams. In the world, it observes the correlation that exists between the values HLD and water cut. Express the result refers to the system with the two oils. The first diagrams the oil with viscosity 19 cp and the second one with the oil the 206 cp. The blue dots indicate that the emulsion was performed at 6,000 rpm and the red dots at 18,000 rpm, and the black curve represents the quadratic fit performance at this experimental point. Firstly, we note that both diagrams present two distinct regions. The positivity HLD water in oil emulsion or lipophilic tendency called normal are found at the bottom of the diagram at the top the inverse emulsion, known as abdominal because the inversion does not follow Bancroft rule or HLD theory. On the water range for negative HLD, oil in water emulsion or hydrophilic tendency cited as normal are folding the upper part for the diagram, and invert water in oil emulsion of the abdominal type are folding the lower part. Type from oil in water to water in oil or vice versa, or increase of the amount in expressed phase are referred to the morphological inversion or catastrophic phase inversion, and the PAP represents the border that separates both types of emotion. In the both diagrams, the results clearly show the influence of the HLD and the rotational speed on phase inversion. The HLD values of the emotion significantly influence the PAP. However, the effect begins more marked for the light mineral oil and for positive HLD. In the first diagram regarding positive HLD values, the number of emotions are considered stable. Following the formulation rules and the surfactant molecules play a role in emotion stability, in this case by static impediment mechanisms. The relationship was more evident in the adjustment present in the first HLD diagram, which examines values coefficient of determination greater than 0.9 for all HLD values and the rotational speed. However, for the second HLD diagram, the R square for the positive HLD system were 0.86 and 0.83 in the 6,000 and the 18,000 RPM of rotational speed applied respectively. Regarding negative HLD values, both fit display in red square values greater than 0.98. The values of the coefficients defining the conductivity of the parabola were opposite. Therefore, for this diagram, first diagram suggests that every positive LRD that is a aggregate value that provides a maximal water cut, in the every negative HRD that is a ARD value provides the minimal water cut value. For the second HRD diagram, the fit suggested for the all HRD values there is a maximal water cut value in function rotational speed, and also the radius water cut value are obtained with the positive HRD. To be dependent on the chemical composition of the whole systems, and the HLD relationship with PAP indicates a good argument. An indication that HLD can be included in prediction models to improve the power of prediction. Besides the chemical effects, it was also observed that both on rotation speed and the oil phase viscosity also affected the PAP values. I would like to thank for the support of our collaborators in the Environment Agency, Unicamp, Equinor, FAPESP, ANP, Alpha, CEPETRO, FEM. Thanks a lot for everyone's attention.